You know when you see a rocket launch and you notice that incredible repeating diamond pattern in the exhaust? Well, that's not just for show. It's actually a visible sign of some unbelievably complex physics at work. A signature, really, written in fire and shock waves. And today, we're going to decode that signature.
A rocket's exhaust is this beautiful, chaotic spectacle, right? But it holds a ton of information. So the real question is, can we actually build a key to unlock it? Can we create a computer model so accurate that it predicts this fiery behavior down to the tiniest detail? Well, that's exactly the challenge a team of researchers decided to take on.
But hang on, why go through all this trouble in the first place? I mean, this isn't just some abstract science experiment. Understanding this fiery signature has some really critical, real-world consequences.
You see, every single rocket plume gives off a unique signal in the infrared spectrum. It's basically a heat fingerprint. And if you can accurately predict what that fingerprint looks like, well, that's a total game changer for defense and surveillance. It means you can not only spot and track any rocket, but you can also figure out if it's a threat, and crucially, pick its specific heat signal out from all the other random noise in the background.
The big problem, though, is that you can't just, stick a thermometer into a rocket plume. It is a brutally hostile environment. We're talking about mind-blowing temperatures, supersonic speeds, and intense pressures all swirling together in this insane, turbulent dance. Trying to study it directly is pretty much impossible.
So what do? If you can't study the thing in the wild, you have to tame it. The very first step in this whole investigation was to bring the rocket into the lab and capture its real physical signature. And here it is. Meet the Ballistic Evaluation Motor, or BEAM for short. It's a small, solid propellant rocket built for one reason and one reason only: to create a stable, consistent, and predictable exhaust plume time after time. This gives the scientists a reliable baseline, what you'd call the ground truth, to test all their theories against. And just to be clear, even in this controlled lab setup, the conditions are absolutely extreme. As the gas blasts out of that nozzle, it's screaming out at over 1600 degrees Celsius. That's hotter than molten lava, and it's moving at more than twice the speed of sound. Now, to see the plume's invisible light, the researchers used a couple of key tools. They had high-speed infrared cameras to record the shape and intensity of the heat. But they also used something called a spectroradiometer, which basically acts like a prism for heat. It breaks the plume's signature down into all its specific wavelengths, revealing a unique chemical fingerprint that tells them exactly what gases are burning up in that fire. Okay, so that's the real-world evidence. With that data safely in the bag, the team started on the second part of their investigation, building a virtual version of the plume from the ground up. They were creating a digital twin. A digital twin isn't just a pretty picture. It's a super sophisticated computer simulation that's built on the fundamental laws of physics and chemistry. Using a method called computational fluid dynamics, or CFD, the whole point was to create a virtual plume that would think, act, and radiate heat just like the real one.
And this is what the computer spit out. The simulation perfectly predicts this complex flow of gases. And it turns out those famous diamonds are actually formed by a series of shock waves. The exhaust gas expands out of the nozzle, right? But then it gets squeezed by the air around it, which creates what's called a barrel shock. That shock then collapses into a flat shock wave called a Mach disk, and then the whole process just repeats itself, creating that iconic pattern we see.
The process to get here was incredibly detailed. First, they had to calculate all the chemical reactions happening inside the rocket motor. Then they fed all that data into a CFD program to simulate the flow of gas, heat, and pressure. And finally, they used a custom program to calculate the exact infrared signature that this virtual flow would produce. Okay, so we've got the physical evidence from the lab, and we've got the virtual prediction from the computer. Now it's time for the moment of truth, putting them side by side to see how they stack up. This is the big one, isn't it? After all that theory, all those calculations, did the digital twin actually get it right? Does it match the real thing? And the answer is an absolute resounding yes. Just look at this. On the left, that's the real plume captured by the infrared camera. On the right, that's the virtual plume from the computer. The structure, the spacing of the diamonds, the intensity, the resemblance is just uncanny. And it's not just that it looks right. When they actually crunch the numbers, the intensity of the infrared radiation, how bright the plume was, in the simulation was within 5 to 10% of the actual measurement.
For a system this chaotic and violent, getting that level of accuracy is a truly phenomenal achievement.
You know, in their summary, the researchers simply state that the results show good agreement. Now, in the very reserved, understated language of a scientific paper, that's basically a declaration of a massive success. It's their way of saying, the model works.
But wait, the story doesn't actually end with a pretty picture. The ultimate goal here was to decode the plume's entire signature, and that includes the part you can't see, its unique chemical makeup.
You see, the shape of the plume, the diamonds, that's all about physics. But its specific color signature in the infrared, that's all about chemistry. So for this digital twin to be truly useful, it couldn't just look right, it had to have the right chemical recipe too.
And this right here is that chemical fingerprint. The dotted line is the real data they measured in the lab. The solid line is the computer's prediction. Each one of those peaks represents a strong burst of heat coming from a specific molecule in the plume. The fact that the prediction almost perfectly lays on top of the real data, that's just astounding.
To get this kind of accuracy, the simulation had to precisely model the amount and the temperature of every key chemical in that exhaust. Everything from simple water and carbon dioxide to carbon monoxide and hydrogen chloride, all while they were violently mixing and cooling at supersonic speeds.
And this, right here, is the final, crucial takeaway. The fact that the simulation succeeded, both visually and chemically, proves it's not just some fancy drawing program. It is a scientifically validated tool that can accurately model the mind-bogglingly complex physics and chemistry happening inside a rocket's fiery exhaust.
What this work really does is give us a powerful new tool to understand things that are incredibly difficult to see or measure directly. And that leaves us with a pretty fascinating thought. If we can now reliably predict this kind of beautiful, fiery chaos, what other complex systems out there are just waiting for us to build their digital twin?